Okay, we're gonna get started, everyone. Oh, good. Well, thanks everyone for coming. It's my pleasure to introduce Andrea Tagliasacchi, who's coming to us from Simon Fraser University, where he's an associate professor. He's also associate professor as a status appointment here in our department, and as a staff research scientist at Google DeepMind. He's been at Simon Fraser before that. He was at Google DeepMind. Before that, he was at University of Victoria. And Andrea is really one of the leading experts on neural representations and neural rendering. He's won multiple Best Paper awards at CVPR, which is the top conference in computer vision. And so, yeah, really delighted to have him here today, and he's going to tell us about some exciting new advances in inverse rendering. So please join me in welcoming Andrea.
And thank you for the invite. If online you cannot hear me, tell somebody in the chat, and I'm sure that maybe Victor can tell me. I have no view over Zoom from my side. So as you can see, the talk title is nothing what advertised. So I was planning to talk about something completely different until a few weeks ago, and then a couple of days ago we did a new paper release, and I told David that I think you guys would have been a lot more interested about this. So I just didn't have time to write a talk abstract. So it's like, title has changed, content has changed, but hey, what do you want me to do? So today I'm going to talk a little about one particular paper, but then the title that I chose was representations for differentiable inverse rendering. And the reason for this is because other than just presenting our paper, I'm going to tell you what has been happening in this general area and what kind of challenges people were trying to solve and what the complexity that was introduced in any of this method was motivated by. And so I'm going to walk you through the history of roughly the last 4 years of differentiable rendering. And yeah, so hopefully, feel free to interrupt me anytime, by the way. I'm happy to answer questions as I go. In general, I'm a little bit obsessed about reconstruction, right? So this is actually a sequence that I think is now published in Google Maps as part of one of the interactive fly-throughs that you can do in I don't know how many restaurants by now. I don't want to shoot the wrong number, but if you open Google Maps on your phone, there's a selection of them. And this is based on NERF, right? So this is actually courtesy of Ben that passed it to me internally, but I'm just like very interested about this general problem of getting a collection of measurements and trying to build some form of like digital replica of the world. So you might ask, why do I care about this, right? There's many different motivations for this problem. The general area in which I work is, of course, 3D computer vision. And now if you think about the history of vision through time, you can think that it went from a setting that looked like that, right? So think about, the early phases of deep learning, right? It was all about recognition, segmentation, instant segmentation, and so on. So a lot of the applications were surveillance, essentially. And in surveillance, is like, other than you having a fixed camera looking at a fixed world, there's not much for you to do, right? So the amount of knowledge that you need to have about the world can be actually relatively shallow. And then, as the years went on and deep learning showed great promise, we moved over to autonomous driving. There was a lot of, in the mid-2010s, there was a lot of talk about how soon that was going to come. It was going to be in the next 6 months or a number of years. And then you can see like the number of degree of freedom has changed, right? So as we move from something that you cannot control to moving something where you can actually affect the environment, the amount of understanding that you want to have about a particular 3D environment goes up, right? And I don't know if you've heard about the massive investments that China's made towards humanoid robotics and all the demos that have been flying over the last couple of weeks online. But if you now think about an agent in the wild that wants to manipulate content and interact with content, you would kind of like to be able to do it without necessarily relying only on past experience, right? So you would like to be able to take raw observations and build some representation that you can then actuate against without necessarily without having seen that object. So I'm going to give you a little bit of a fly through very quick of papers over the last, I'm starting from 2009, so roughly like 15 years, okay? So, in the realm of 3D computer vision, right? So we started this voyage, let's say around 2009, when essentially the problem of calibrating cameras from large collection of images under some conditions was essentially solved, right? So this is a very famous paper, Building Rome in a Day, done slightly south of where I am right now. And you could build a sparse point cloud given a large collection of images, potentially taken a different time per day. Right, so I would say that this moment in time marks when mostly camera calibration is a solved problem. And then after this, there's been a lot of developments more in the real-time SLAM, so how to retrieve camera poses in real time through some devices. So the type of 3D understanding that we have back here, as you can see, is like this sparse point cloud, right? We didn't really have a dense reconstruction. If you wanted to get a dense reconstruction, I challenge you to have success in that by opening up CoMap and trying to build one, and then being a little bit disappointed. Yeah.
But I mean, one of your colleagues, right, had worked on multi-view stereo.
Right.
From even before that, right?
Yes.
So I mean, there had been work.
Oh, there is definitely tons of work. But what I'm saying is that at the time, like this is more the sparse view, and then the most popular technique for dense reconstruction came with the advent of depth sensors, right? So if you work in robotics, Kinect fusion and real-time fusion of information to build these dense 3D maps were basically the dominant technique in especially in real-time applications. And then if you see again these representation, however, they're only mostly focusing on the geometric part, right? So the problem was solved to a certain extent, but not to the photorealistic reproduction of content. And then meanwhile, on the graphic side, you have techniques like Poisson reconstruction, where you could take large collection of points and building extremely high quality surfaces representing the data that you had in the backend, right? So this is like until the advent of NERF, which is going to come in the next slide. This is kind of like the status quo on how you calibrate images. You get a sparse point cloud. You could use multi-view stereo to get a dense reconstruction, which is what then powers Kinect sensors or depth sensors. And then you can fuse this information to get a full reconstruction of the scene, right? And then a few years ago in 2020, where this history comes or starts, NERF came to be, right? So the idea was that you have a 3D representation that is volumetric in nature, and you associate every pixel with information along the entire array. Okay? And these allow you to take a 3D representation and send gradients from the image space throughout the entire volumetric media, and allow the model to train much more effectively than if you were trying to reconstruct a surface directly. And the 2 bits of technology that unlocked it, ironically, was not a neural part, so you can drop the first keyword from the paper, but the 2 bits that actually contributed to getting these great results, the first one is the modeling of view dependence effects. So the ability for the model to encode the visual phenomena that you see on the video on the left effectively, which you can see them actually here. So this is this is the same scene, except that I'm keeping the camera virtually static, and I'm showing you how a position in space change in appearance according to the position where you're looking at. And this shows you that to represent data in the wild correctly, it's very important for you to be able to model view-dependent effects. Right? So that was one of the key components of the original NERF paper. And the other key component is what I mentioned a few seconds ago, was the ability to use volume rendering to send gradients back from image space all the way through the entire volume, right? If you think about the comparison between non-volume based rendering effects, where you send gradients back in between a pixel and a single position in space, that would require a lot of local optimization to converge, and that was the different way of doing it. So since then, there's been an explosion. We are in need of an holiday. If you work in this area, you have been too busy. It's like Daniel used to joke, it's like if you work on NERF, holidays are not part of your life, at least until you're done your degree. But this gives you an idea of what happened in between 2020 and 24, right? Like these techniques were expanded in every direction imaginable. And here it's actually an incomplete list. These are some of my favorite papers in the various area. There is a big thread. Meta typically tends to dominate this area where they study dynamics or 4D representations for W synthesis. There's a part on studying, aliasing problems and Fourier analysis and multi-scale representations. Very nice works actually from David Year as well, if you have not read it. There's been work on generative modeling, how to connect the 3D representations with 2D generative modeling, and even train them end-to-end completely without requiring any backpropagation at test time. There's been better training, either architectures or optimization techniques. Actually, this is another paper from U of T that is on my top reading list right now in terms of learned optimizers from Raquel's lab. There's been work on predicting models rather than optimizing, go directly from images to the underlying 3D representation, and this falls within the formal models. We've done a bunch of work in terms of building 3D representation more robustly in such a way that is invariant to aberrations in the data, distractors, people that walk in front of your camera, and so on. There has been a lot of interest in extracting meshes. I would say that within Google, when NERF first popped up, everybody was asking about this. That's the only thing they care about. How do I get a mesh out of my NERF? That was the day zero question when the papers came out. There's been a lot of work, not a lot. There's been some work actually on quantifying how well you can construct a representation from images. We've done some similar work in base race with LRT and some other works from, I don't remember, university. And then there's been also very interesting work actually. Where is Ben? Like, this is for, I didn't know you were here, but so here you have, Transient Angelo from David and Torf, and there's others that don't have a short acronym, so they cannot end up on the slide, by the way. Otherwise, I would have put more. But all sort of like ways of building basically programmable cameras in some sense by accounting for the image formation model directly within train. And then finally, there is the hybrid representations, right? And I've been playing around here a fair bit, right? So you have things like mobile nerve, we'll discuss it later, ways of integrating textured representations within differentiable rendering and so on. So now there's a bunch of extensions, right? And there's like hundreds of papers in this topic. But if you zoom out a little bit and you analyze history, a lot of what people cared about was this. Okay, so there's two main axes that people really were passionate about. The first one was that if you consider the basic NERF model, it was incredibly slow to train, right? It would take you like a day roughly to get a scene, and it was a small scene as well. And the second one is that despite the fact that the representation that you built was of very high quality, you could not serve it. And so if you now imagine that you are, Google or Microsoft or Apple, not being able to serve a high quality 3D representation is a problem, right? Because it's like, okay, what do I spend all these flops for if I cannot render it efficiently? And so rendering speed, or you can think of this as training and testing. Testing and rendering here are the same, was also another axis of like a principal axis for exploration. And so now there's been, I'm going to show you, and every paper in this chart has actually won an award or a nomination for an award. I think that was ours was actually the lowest of the pack. Actually, no, it's not true. NERF was also an honorable mention. You didn't win an award either, but almost everything. So the first one was Instant GP, right? So Best Paper Award at SIGGRAPH 3 years ago. Okay, and the idea was that rather than using MLPs, you will amortize part of your model by leveraging memory rather than compute. Okay, we're going to mention this quickly later. And then we went on, okay, we could train models efficiently, but the problem is that, okay, if you want to now serve these models, you can train them on the cloud, that's fine. But if you want to serve this model to a customer, then what do? Do you go around with a 4090 backpack with a heavy GPU and then stream the media to your phone? You're joking, but that's actually what the Google Maps model was doing. It was a GPU in the cloud, and it was streaming live footage video to your phone. Okay, so you think it's crazy? Actually, no. It's actually what was in production. Still in production, I think. I'll have to check. It was still in production as of July. I can guarantee that, though. And then here where we came in with mobile nerve, where the idea was that, okay, no, we're not happy with only rendering efficiently. We also want to be able to serve model efficiently. And this leaves clearly a gap up here, right? So can we get now a model that is not only efficient to train, but that is also efficient to render, and hopefully where you have a single execution pipeline that gives you both at the same time? Because what I haven't told you is that mobile nerve worked, work at 60 FPS on my scrawny iPhone cheapo, the SE version, SE2, I think, but required a distillation phase, right? And so the training time and the testing time at the distillation phase in between, which is ugly to have, right? It's more parameters, more fine tuning, more source of error, and so on. And so here is really what was the elephant in the room is like, what went right here? Oh, there's no mouse. So what went in the top right corner of this diagram? And that hole was filled by, as you know, 3DGS. Okay, so 3DGS gave you a single representation, and the tricks that were used again was the one of rendering and rasterization that gave you simultaneously a single pipeline that simultaneously gave you high training speed and high rendering speed on consumer devices. So within a few months of it publishing, there was already like real-time viewers that you could find online from Luma, for example, that achieved this. So as I said, it's like part of this talk is more like educational. I decided to do a weird one, I guess, this time. So let's take a look at why, how do you build this diagram and how it was solved in exploring the various direction, right? So the first one, as I said, was NERF, right? The reason for which it was slow is because you might have had a 3D structure like this loader. Thanks to Waki for this slide, by the way. However, every time that you need to query your representation anywhere in space, you pay the cost of executing the entire representation. And the representation was an MLP, which means that any querying point that you wanted to take, you needed to execute the entire computational graph. So there was no locality to the representation. Okay? And so this is why it was bad, right? So the whole scene was represented in a single network that could not be partially executed. Maybe there's a solution to that. I have not seen one in terms of sparse execution. So how do we get away from that? What was instant NGP, right? So instant NGP trade off using a small neural network and then storing a part of the computational burden in memory by storing features on hierarchical grid representation. Okay, so that was the trade-off. And so you didn't have to execute such large MLPs, and so your training time went through the roof, right? Orders of magnitude faster. So that was phase number 2. So again, we're still in the volume rendered domain right here, okay? And if you want to do these things, like you can get a few frames per second of work performance on a high-end GPU, but the question is like, okay, if that's what you need, you need to execute this architecture. What you need is that you need a CUDA GPU, right? And how many of you have a CUDA GPU on your phone? And the answer is that unless you bought a CUDA tablet in 2015, as I did, probably you don't. Doesn't exist anymore, by the way. So you can't, right? So the solution to this problem is something that we proposed back in 2015, which this was mobile nerve. And the idea was very simple, is that if you actually look at the volume rendering equations, there is one particular node, and you can take a look at the volume rendering. When the opacity of your volume rendering equation is binary, at that moment, when you make the opacity binary, the volume rendering pipeline and the rasterization pipeline match. And so what you can do in a distillation process, what you can do is you can take your continuous function, right, that might have non-binary opacities, and use tricks from network quantization to binarize these weights to be either 0 or 1. And once you do this, you can actually get, as it was playing a second ago, you can actually get real-time performance on my scrawny phone right here. And then finally, as I said, is like these techniques of using, or these ideas of using rasterization for accelerating rendering were then ported to the training part of the domain, right? So this is exactly where Gaussian splitting came in. And the idea was that not only we're going to use rasterization during testing as we render the scene, but we're also going to use rasterization during training. And in particular, this was done by representing the scene, as you can see right here, as a collection of Gaussians, anisotropic Gaussians in the domain, and then exploiting math from roughly 2 decades ago that allows you to take the shape of a Gaussian in 3D and then splat it to its 2D counterpart in a differentiable way. As you can see, like the main speed up in terms of accelerating training and rendering came again from rasterization and being able to perform these efficiently. So now what does that mean in terms of the paper and the 4 ones that you had on screen? By the way, I'm going to use George's photo, but I could use Kerbal's photo here as well. I cannot put 2 people. But this is what it meant, right? It just meant that, a lot of the work in this area was just completely done, right? And then you have to move on to whatever was next. So if you were me, having just launched Mobile Nerve about 6 months earlier, it was a pretty sad moment in history. And at the time, we were actually working on this follow-up paper, Quadrature Fields, which was actually going to resolve a lot of the problems of Mobile Nerve and bring it on par with what a splatting model could do. But George was about to come with a sequel to kill that project as well. And so we still finished it last year at CVPR, but moving on, right? Like he showed us that something better existed. It's time for revenge. So, however, right? So George and what's Kerbal's first name? Bernard, right? And Bernard introduces Gaussian splatting, but again, we have yet another elephant in the room, right? So sure, you're going to get a model that trains and renders efficiently, but it doesn't mean that it does everything that you want to do. And here I'm going to show you a laundry list of things that actually don't work. So for example, compared to a nerve-like problem, a 3D Gaussian problem optimization is extremely brittle with respect to initialization. And for example, in this MCMC paper that we had at NeoRIPS in December, we actually addressed that problem specifically. Then, for example, it's like, okay, fine, nerve, you could convert it to a surface model for extraction of surfaces a posteriori, but 3DGS doesn't really give you that level of control. And the few attempts at realizing this goal, like Sugar from either Graz or Bordeaux, anyway, Vincent Lepetit's group, and 2DGS from Andreas Geiger, kind of get you there, but as a person that worked in 3D vision reconstruction for a decade, I wasn't so convinced, okay? So maybe. Or how to avoid popping artifacts, right? So if you take these 3D represent, I'm gonna show you later, they actually have artifacts that you have to remove, right? And you will see them according to this, I'm gonna just show you later. And then the other one is like, okay, fine, but if you think about these, neural rendering model, what you would like to do is that you would like to approximate the rendering equation, but the rendering equation doesn't just have emissive light, it actually has light bouncing around in the steady state, right? Or after steady state executed. And so how do you model secondary bounces and all these things? And people have been doing work in this area. So for example, as I said, this thing is electrified. Maybe it's the carpet. It's the first shock that I get. Keeps me awake. All right, so this is an example of the MCMC solver. So on the left, you see a 3DGS model that is initialized from noise, okay? And which means that it's not initialized by core map, the sparse point cloud that I was showing you earlier. And you see the training model completely collapse when the model is not properly initialized. And what you're seeing on the right, on the other hand, is that by modifying the solver to make it work more effectively, by introducing noise within the optimization, you can actually explore much better the optimization landscape. That was one fix, right? I'm just showing you the laundry fix, the laundry list of fix. The second one was that I mentioned was 3DGS, right? So rather than using 3D splats, they use 2D splats. They orient them to make them face essentially in the direction of the normal of the surface. And then they use some tricks from Kinect Fusion, one of the papers that I showed you earlier, to then fuse all this information, fuse all of the depth maps in a single 3D representation. As you can see, there's a lot of ideas from older days, right, that get brought back to fix some of these issues. And yeah, it looks quite nice, but I'm, again, not fully convinced. Or then if you want to go to solving popping artifacts, Bernard and colleagues from Graz built this paper. You can actually see popping in action right here. So these two Gaussians in 3D, they're organized in this way. But the sorting of 3D Gaussians in the kernel is done by using the mean and projecting along the view direction. And so now as you're slightly rotating within the view, the order of the two Gaussians suddenly changes in this discontinuous point, and this results in the popping artifact that you see on a simple case on the left. And you can actually see them right here on the right. Right? These are kind of like exacerbated in terms of like highlighted by the authors of the paper, but you can see actually these virtual popping artifacts that you will see in the renderings. And they found out some ways of solving this problem, modifying the sorting, adding a two-stage sorting, quite complicated, adding a tile-based pre-sorting, which is basically this one, followed by a local resorting that makes sure that these swaps will not happen. Anyway, many different ways. Another way of doing the same thing again is Ever, right? Did I get the name right? And so Ever, for example, replaced these Gaussian kernels with solid constant density ellipsoids. And if you do that, you can again solve for volume rendering, and you can actually get a representation, which you can see down here, that doesn't have the popping problems that the original ones do. But to do that, you then have to plug in, again, yet another NVIDIA library, which means that this problem is only artificially solved. Because it's only solved if you are on an NVIDIA GPU. And now how do you get this solved if you now are in a consumer level device? And then there's more work. Now we're going to enter the U of T series of work. So very interesting work from the NVIDIA lab here in Toronto. And the idea is like, how do you get ray traced effects within these representations, right? Again, same recipe that you had a second ago. You build the bounding volume hierarchy with optics, this library for ray tracing, and then you pay a fairly significant cost at render time to then traverse the representation to generate an image. However, what you can get is that you can actually get a representation where you can now insert new objects, and the behavior of light within the scene looks pretty realistic, right? But you have some fallbacks. And in particular, it's like you're going to have to use the library for every ray that you render within the system. Okay, so that's maybe another way of solving it. Same group. So the first author is the second author in, well, maybe not. They were both Spanish sounding, but never mind. I thought this one is the same author as the previous one, but it's not. And there's other ways of doing it. Again, using more sophisticated ways of projecting Gaussians to screen space. But now I'm just showing you a collection of tricks, right? So, Bernard and George brought in this representation, but now to get it where we want it to be, there is a Band-Aid after Band-Aid after Band-Aid after Band-Aid applied on top of it. And then the complexity of the underlying ecosystem keeps growing over time, right? So if you really want to get something that really tackles all of the problems simultaneously, do you have to live with these Band-Aids? And so my point is that if you actually go back in history and ask yourself, okay, all of these point-based rendering pipelines, where did they end up? So on the left, I took a screenshot. So this is the main conference for publishing results in point-based rendering. So I started my PhD a little bit after that, so I was familiar with this because it died. The entirety of point-based rendering, it was all the rage in the beginning of 2000s, and then a few years later, completely disappeared from history. The entirety of graphics moved away from it. Still, once in a while, you find the odd paper, but didn't find any adoption. So you might ask yourself why? Because points are not the workhorse of computer graphics. Meshes are the workhorse of computer graphics. You can do whatever you want, but if you cannot get to the mesh at the end of the day, your technical artist will say, yeah, but now how do I get a mesh out of it? So I told you, that was the first thing that everybody was asking when Nerf came out. So how do we solve this problem? And the idea is if you actually look back at, as I said, the paper that in my opinion, killed this area, because it gives you a very elegant way of converting collections of oriented points into surfaces, was Poisson reconstruction, right? And Poisson reconstruction still has a volumetric formulation, and at the same time expresses surfaces in terms of zero crossings of some level sets. So what are we going to do? I'm going to present you this paper. Now, I love this animation, by the way. We spent an inhuman amount of time deciding how to visualize this, by the way. You do not understand how much time we spent and how many iterations of it we did. So I'm going to present you this radium foam paper, which we finished recently. This was a huge effort by Shri and Daniel. To give you an idea, at the start of the project, I told Daniel and Shri is okay, we want to do this. It's it was a bit of history. It was another project that we were working on. It was connected anyway. So it's I was telling them, okay, guys, yes, this will work, but this will be my ballpark was a year to a year and a half of brutal CUDA coding. Boiled down to 9 months of brutal CUDA coding, but the estimate of where this was ending up was fairly correct. But they did a spectacular work on it. And I hope you will appreciate the work that I've done, and I will do a good job in showing it to you. So how do we go from a representation that we can trace to a representation that we can learn effectively? So remember, the core recipe that I told you earlier was the recipe of volume rendering. We don't want to give that up, okay? The volume rendering is key. So now you can take a look at the equation that are in their undervalue of Nerf, right? So equation of the undervalue of Nerf, you can think of your representation as being a cloud of light-emitting gas, right? It's like a cloud of smoke that emits light in several directions, and this light is view-dependent, although this equation doesn't reflect the view dependency considerations. So you can work through this math, and you can discretize it, and it boils down by making some assumptions on the fact that the density of this cloud of smoke is constant, piecewise constant, and that the radiance emitted in a certain region of space is piecewise constant. And then you get to the equations that you might have seen in hundreds of Nerf papers. Okay? So if you want to know where the first one and how to get to the second one, by the way, Ben and I wrote a cute little tutorial. I was very confused by those equations when I saw them. It's no, something is wrong there. No, it's not. We went through it very carefully, and you can read it there. But now, the question is that you have to ask yourself is what was this designed for? So there was another technical report before this one, which was a bit more rough around the edges. But if you actually read it, what was this equation actually designed to do? This equation was designed for essentially medical applications, to be able to render a volumetric tetrahedral mesh to screen space. What it was designed for, it was designed for this. It was designed for you to, right now everything I'm doing, by the way, all the illustrations are in 2D. Sadly, I cannot draw in 3D, or it would be impossible to see anyway. So I'm just going to use slices, right? And all the math is identical, by the way, so there's no reason to worry. So this is just a triangulation of space, okay? And that math that I showed you in the previous slide, this math right here at the bottom, is designed to volume render structures that look like this. And these structures are called injective mappings of space because it means that I have for any point in space, for any point in a triangle, there is a single triangle that maps to that point. I guess they're bijective from that point of view, although you don't have to cover the entire domain, so they're injective actually, so never mind. Okay, so you want to maintain this one-to-one mapping, right? And so the way in which that equation executed is that you trace the ray through your media, and remember, you have a piecewise constant assumption. And you can make a very simple piecewise constant assumption in this representation, right? You could say that every triangle that is found along the ray, within the triangle, the density and the view-dependent radiance is constant. This is what the model I showed in the previous slide was designed to do. If you read the original technical report from the 70s, that's what it was designed to do. NERV is not doing this. The underlying representation of NERV is not an injective partition of space. It's using this piecewise constant approximation to the integral, but it's actually not doing it in a correct form because the segment over which you discretize the integral, they're actually proposed by a secondary model. Well, in this case, you know exactly what the segments are, right? When the ray intersects this polygon, you know that you're going to integrate a constant for this length. And the quantity is exactly constant across the media. So there's a bit of a mismatch, right? So NERV was kind of like breaking volume rendering along certain angles, despite the fact that it worked. Okay, so now we have this representation. And let's say that I define a density and a radiance per polygon, right? And I backprop so that when I integrate, so when I execute that equation along the green line, I get a particular color. Okay, so sure, I can modify density and radiance easily to obtain exactly what I want. But now the question is that if this is the representation that we want to use, because this is the one that respects the physics that we built upon, what we also want to do is modify the position of the sites, right? So we would like to modify essentially the discretization points of our piecewise constant field to then improve the quality of the representation. Fine, you can do that. You can plug into gradient descent, and now you can ask yourself, is like, okay, if I now do gradient descent on this quantity, what could go wrong? And trust me, things will go wrong. I coded this up in 2011. Yeah, I'll give me a couple of beers and then I'll tell you the gruesome stories of how many months I spent debugging. So what will go wrong? The primary thing that will go wrong is this, right? So imagine that for whatever reason, your volume rendering equations gave you a gradient, and this gradient told you, okay, you're supposed to push this vertex over here. And assume that that's the only gradient in the system, right? So that's the only change you have to do. So what happens is this. So suddenly you have a representation that by construction was giving you an injective parameterization of space, conditional to which volume rendering was doing the right thing, and now you broke it. Now you can't execute those equations anymore. This parameterization is invalid. Who knows what is going to come out? Some garbage of form. Yeah.
How do you even decide on the discretization in the first place?
I'll get to it. Yeah, I'll get to it. Although you reminded me that I should probably have a slide where I show it being built at runtime. Yeah, anyway, I'll get to it. All right, so although maybe the next question actually boils down to part of the answer now that I realize it. So another question is like, okay, fine, if this is not the right discretization, so let's say that the vertices you know where they want to go, right? Then you might say, well, but this mesh is not good. I could remesh the structure to fix this problem, right? I could do local remeshing ops to fix that problem, right? Sure, you can, right? And perhaps there is then a way of, rather than controlling the topology of the structure manually, there's a way of doing it in an implicit way. So you don't have to manually go in and modify things, but there is the connectivity of the graph is given to you as a function of the position of the vertices. It exists, by the way. Right? So rather than saying that I'm going to control my mesh manually by deciding where the vertices are and where the which triangles connect, I'm going to say, no, my topology is going to be a function of the position of the vertices. And this structure in computational geometry exists, and it's called the Delaunay triangulation. Many different ways of looking at it. Daniel likes this one, so we have this image today. So if you have a collection of vertices in the environment, a Delaunay triangulation puts a triangle whenever you take 3 vertices and the circumcircle of these 3 vertices is empty, that means that the 3 vertices are connected. 1, 2, 3. So as you can see, this blue circle passes through 3 points, no other point is in it, and so I'm going to connect those 3 vertices with a triangle. So this is called the Delaunay triangulation, and you can see the outcome of the triangulation on the right. And the topology of this works both in 2D and in 3D, and the connectivity of the graph is automatically computed for you. There's like classical algorithms. Apparently, we invented a new one in the middle of this project. We're going to have to find out whether we're going to have to write a computational geometry paper as well now. It's unclear. I thought that Daniel implemented something, and then yesterday I was asking, he's like, no, I rewrote it. I put something else in it. We'll find out. Supplementary material, we'll say something about it. Yeah, Daniel's fine. Hey. So we have this, right? Now you say, okay, fine, we don't have to worry about topology. Topology is automatically computed. Now, as far as decide where to put vertices in the environment, I'm not going to have to do a lot of work, right? Yeah, there's a problem. Now, you ask yourself, is this representation differentiable? No. Why? That's why. Right? So you can cause epsilon shifts in your triangulation, and if you happen to be in the case where 4 points are at these like empty circumcentrals, you're going to have an edge flip happening at that configuration. And so now imagine that this is, a representation where you have piecewise constant representations in some of these vertex spaces. And what happens when you flip it? Which value do you put where? Exactly, what is going to happen right there? And so the question is that now if we build a differentiable model on this, it's not going to work particularly well. So we're going to have to do something else. And I think what that something else is actually quite neat. So the Delaunay triangulation, which is what we've been using until now, admits a natural dual, which is called the Voronoi diagram, which if you have never heard of this, but you've heard of k-means, it's basically the same thing. You can think of it that way as well. So if you have executed ever k-means in your life, you more or less have also executed a Voronoi diagram. The math is very similar to some approximation. And the duality relationship, you can see it right here, right? So whenever the Voronoi diagram is every cell contains all of the points that are closer to this point than any other points in space, okay? And the duality relationship is that every time that I have an empty circumcircle, I apparently do not know how to pronounce that, this point right here will become a vertex of the Voronoi diagram. So that's the duality relationship in between the two. And as you can see, it's made of convex cells, and it gives you an injective parameterization of space. So seems to be something cool, right? Convex media is easy to work with, and what was the other thing I said? And the injective parameterization is exactly what we need for volume rendering. Cool. So now let's compare exactly the little demo that I had earlier with respect to perturbation. Now the representation is differentiable, right? Because if what I'm doing, for example, is tracing these rays and then integrating quantities along the array, as you can see, this value of the constant, as I'm moving the site, smoothly enters the optimization problem. It's not a discrete flip anymore. Which means that now, as far as I can compute this Voronoi diagram efficiently and maintain its topology during the training loop, the whole underlying representation remains fully differential. Yeah.
But there are changes in the number of vertices and the number of edges at the boundaries of the cells, right?
Yeah, but we don't care because the cardinality and the topology of those never enters the system. So it's so the only thing you have to do is that I wish I could pause it for a second. You can imagine the transition moment, right? As an epsilon segment from this quantity enter the system, your density will increase by an epsilon amount compared to the density stored within this cell. So it's a smooth, like the degree of freedom gets added very smoothly within the optimization in a continuous way. So actually we had an implementation, I think it was around August. We thought we were done, and then we were doing that, and then you would see the losses and it would shake. And we were trying to understand what was happening and looked at the training loops, and you could see these happening on the surfaces of the object. There was all these edge flips happening. And yeah, it's not, it doesn't give you a very stable solver, basically. It gives you a very noisy solver. You can still do it, and there's ways of fixing it. If somebody wants to work on this stuff, let me know. There's another paper from, again, the 70s that I would like to put up that will bring you back to the thing on the left, but without some of the problems, but that's another story. Well, clear up to now? So now the question that you should ask yourself is like, why on earth did I call it a radiant foam? So it turns out that if you take a bunch of bubbles, okay, and they're in the stable configuration, I spent an entire afternoon making bubble fluids to actually generate a compressed bubble formation to actually match these two. My bubble fluid needed to rest for 24 hours. So unfortunately, I had to find a picture online of 3D bubbles, and we're gonna live with it. So if you have a lab set up, I would be very happy to do it. But you can kind of see right here. So here, actually, the pattern that you have, I made it roughly match. And what happens is that if these are actually compressed bubbles between two surfaces, these interfaces will be almost like perfectly flat, right? Because the pressure within each bubble is constant, and so you have equipressure on each side, and so you end up with a length minimizing curve in between the Voronoi sides of the bubble. And so you get something that looks like a Voronoi diagram. And that's why it's called a radiant foam in terms of the paper, right? Because it's a foam, because the Voronoi diagram essentially is modeling reality, is modeling 3D as a million bubbles scattered throughout the entire world. And it's radiant because within each cell of the Voronoi diagram, you have a radiance field, right? So you're going to have a density, and you're going to have a view-dependent radiance. Okay? So now the question becomes, let's see, 1 times 52. Sort of 10, right? Just okay. So how do you render this thing? Because for now, all I gave you was a very expensive Voronoi diagram computation and a very complicated to code Voronoi triangulation and maybe a dual in between. So it turns out is like, how do you render a mesh? And in particular, how do you render a volumetric mesh? Forgot a citation here at the bottom. There was a paper written by, I think it was 2005, that shows you how you can actually render quite efficiently in a shader a mesh by simply walking along the ray. So as far as the connectivity structure of your injective volumetric mesh is known, you can literally, when you're within a triangle, you can query what's the next edge, traverse it until that point, and then query the next edge. And that's it. So now we're not going to work with triangles anymore. We're going to work with Voronoi diagrams. And now if I give you this Voronoi diagram mesh, how do you ray trace a Voronoi diagram? If you have the connectivity structure in the underbelly, you do exactly the same thing. This is a better animation. This is done by code, by the way. The previous one was done by my painting. So there is one caveat. This paper was designed for polygonal meshes, not for convex meshes or for convex cells. So there's one extra tidbit of very small piece of math that you have to do. So let's say that you're in this configuration. Let's say that you identified, you were in this cell right here, and you identified that this was the cell to trace next. And the quantities that you need to render are the length of this segment, where it should go next, and the radiance and density contained within the cell. Right? So we already have those two because we know that this is going to be the next element along the tracing. Now what we're going to have to do is we're going to have to determine the position of this point and the position of this point. And then we're done, right? That's the only thing we need to render. And this is, I was actually afraid to not do enough math today because it's like the technique is just so simple in its underbelly, close parenthesis. But the way in which you do it is actually super simple. It's like what you can do is that you can split the collection of facets along a convex cell in the set of facets that is facing the ray, right? So the ones with a normal that point towards the ray, and the collection of facets that point away from the ray, the green ones. And then what you can do is that you can call the entrance point within a convex cell as the plane that is furthest along the ray in between the forward-facing cells. And the exit point will be the closest, so this one, in between the hyperplanes that intersect the ray as I'm exiting the cell. And that's it. Now you can extend this algorithm that was designed for polygonal meshes to then trace convex cells efficiently. So now how do you train this entire thing? So now I gave you the forward pass, right? So how do you train the entire thing? It's actually like very simple. Like the RGB loss is literally the nerve loss, nothing special. And the only thing we have to add is that we have to add this quantile loss. don't even look at the math that much. What this does is that it tries to promote the existence of Diracs of density along array, right? So it basically tries to make hard surfaces somewhere within the environment. And it's the same loss that papers like Mipner 360 introduced to prevent floaters. So it's exactly the same loss. With the difference is that this has a constant time of execution versus the one of Mipner or Mipner 360 has a quadratic execution cost, but other than that, it's the same. So now if you do that, you're gonna have to train. And then maybe I'm answering your question right now. As you're building the representation, what you want to do is that you want to add new sites, because every time you add a new site, you're going to increase the representation power. And so what we do is that actually we measure the amount of error that a site is causing to the rendering. Let's say that we found out that this site is responsible for all of the error in terms of gradients in image space. So that site could use some help. And then again, same thing, when you're building an optimizer, you want to make sure that any change you do to the representation is as continuous as possible. And again, there's a super cute thing that comes from boundary diagrams, is that if I now take a site and I do a randomized split of the site in two random directions, right? Or you choose a direction and you do an epsilon split, the cell splits perfectly in two. And if you now put the same density and radiance to these two cells, the representation before the topological change and after the topological change is, from the loss point of view, you cannot even notice it. It's zero. Right? So that's actually how you densify the representation. You're observing the error that is happening within your scene and figure out areas that need more cells to exist, and you just do cellular mitosis, essentially, to insert more. So that's one. And then the counter side would be like, I put too many cells in an environment. For example, I'm in empty space. At the beginning of training, I didn't know this was empty space. There's too many sites right here. I want to remove them. This is a little bit trickier. You cannot just remove an element because it doesn't contribute to the rendering equation, because the problem is that an element affects the interface that the neighbor has with the environment. And so what you have to do is that you have to detect groups. So an element and its neighbors are not supposed to contribute to the rendering equation for it to be removed, for the center guy to be removed correctly. So it has a chain-like effect, but this works very well. And so if you put all this chain of ops together, you get this. So this is a live screen grab from our workstation, where you can see like it's 200 to 300 frames per second according to the moment in the video. It's a full resolution, and this is exactly what is executed in Render Valley. We're tracing bubbles. So now you might ask, okay, until now I showed you only 2D visualization of the entire thing, which is what we've been discussing for most of the year on the whiteboard. And you might have seen this online. So what I'm gonna have is that I'm gonna have this laser light right here, and I'm gonna slice the Voronoi diagram along this plane passing through this line. And I'm gonna show you the internal of the representation. And slicing a convex with a hyperplane gives you a convex, so it's again a convex diagram. And as you can see, the amount of cells when the laser line crosses the table, you can see the density of cells in the proximity of where you need information has increased because, as we said earlier, we densified the representation where needed. I stared at this video for so long, but all right. So now, other things that are cute to see is how does it train? The training modality is very similar to the one of a classical nerve model. You start from something that is almost everywhere transparent, because then the volume rendering equation can spread gradients through entire volume. And then as the model is training, the surface solidifies over time. And you get, I think right now it's done training. So I'm going to show you one more. Now that I've explained it.
What's training to it?
It's a little bit more than Gaussian splatting, but we haven't really spent a lot of time in optimizing anything. It's not my priority, to be honest. Just curious. Yeah. The other people are doing it. I think that's a good part about this. So somebody's writing a WebGL viewer for us. Another person is writing a Slang implementation of the entire thing. So we don't have to do it. We can do something else. There's less engineer. And so now what I'm going to show you. So the next visualization is going to show you actually the the expected depth computing from, so it's a similar visualization. The first diagram right here is where basically the ray terminates. I'll play it once more. And the second one is the number of cells, the number of Voronoi cells that you cross during rendering. And you can see that despite the fact that we, cross in average roughly 100 of them, this doesn't prevent you from rendering efficiently.
So I assume you attach there's some view dependence of the appearance, right?
Yeah. So every cell has a spherical harmonics, and yeah, you query it, condition it from the viewpoint, and then return the color. Very similar to planoxels, and very similar to Gaussian splatting as well.
One general sort of observation that comes to mind is if you don't have this view dependence, you just look at it purely from the independent perspective. That boils down to solving a standard computational tomography problem, where you're trying to assign to every point in a volume a transparency. But you add an L1 prior, which basically enforces or promotes piecewise constancy.
It's not a tomography because it's actually not a sum. There is actually. So let me.
That's the volume rendering equation, right?
Yeah, and so there is actually occlusion, right? So it's not true that if you have low opacity further down the ray that you will actually get to the area, because you might get occluded completely. Your transmittance might be 0 by the time you reach that position. So it's not tomography. Like sometimes we code this up as tomography for debugging, sub bits, but in general, this is not a tomography kind of like rendering equation.
So it's not strictly a sum. There's a
no, it's not a sum. Yeah, you accumulate. You can think of it as a sum where you accumulate the amount of density, and then the more density you accumulate, the more of transmittance you lose. Right. So you start from 100% transmittance, and then you have a monotonic decrease in transmittance. So there's a point when your transmittance is 0 where you're occluded because you're behind an object, and behind that point there is no gradients propagating anymore. I have let me show you. I have a video specifically for that. It's just on a different website. I didn't put it in the slides, but if I show you, it will be trivial for you to see. Actually, Lily she's nodding.
How do you get a mesh from it?
Can I not answer that question? We're working on that. That's literally what Sheree is doing right now. So we started his next project now. We already had bits of it coded up and implemented. There is this part right here of getting regularizer done right, plus a bug, plus the fact that we weren't working in Deloni, we're working Voronoi space. Those are the three main things that held us back for a while.
Do the edges in the Voronoi partition roughly align with the surface, or not really?
Not necessarily. Okay. No. It would be nice if that would be the case, but
I have a question. So you're 650 gray for each pixel, right? How come do you have any aliasing? Because I think that was
we will. So we haven't worked on the aliasing bit for this paper yet. We didn't need it. I forgot in the last discussion that we had. My sleep deprivation is kicking in, but I forgot if the last discussion that we had was that beating the most recent paper in Gaussian splatting was caused by aliasing or was caused by something else. So yeah, it's right now I remember. So we were bickering in the project meeting. Is like Daniel is convinced that the reason that to get correct surfaces we need to solve the aliasing problem. I'm not so convinced. Just because there's been other examples of. There's no aliasing consideration whatsoever right now. It's one of the typical follow-up works that people work on next. So 0 consideration for aliasing. So all the cameras are roughly the same distance in the scene. Yeah, we haven't done that bit yet. We were working on and I think even the core bit, there might be like small changes that make it work better. So yeah, we're not quite there yet. So we get to it, just maybe somebody else. Now the cool thing is that this is a ray traced representation. It's not a rasterized representation anymore, right? Because we're walking through cells, which means that now to get all, how many of you took graphics? Like intro to graphics? Okay, not that many. So when you learn graphics, you learn a very simple thing. Rasterization, what is used in games, is fast, but to get advanced visual effects is a pain. With a pain with a capital P and all the other letter capital as well. Ray tracing is slow, but getting high level, like advanced effects is basically trivial. And so you get this dichotomy of words, right? And so Gaussian splatting lived in the game engine rasterization dichotomy. It was very hard and annoying and difficult to get these advanced effects. We're living in exactly the opposite side of the world, where ray tracing is dominating. And so that means that, for example, we can add a random object within the representation, and then we can just bounce our rays around whatever thing we want, and now capture a secondary ray effect with no work whatsoever added to the workload. Or it means that we might have, a problem where we also want to learn about refraction. So now the bow, these are all spheres because you code them up in one line of code, by the way. That's why they're spheres. But you might have a simple sphere, and now your rays can actually traverse the media being refracted along the surface of the object. Again, no changes of the code. If you want to do this in rasterization, fair amount of pain. Or the one that I was more interested in, I wanted to move away from classical pinhole cameras and classical phone cameras. I want to go to 360. And yeah, oops, what was that? It works, no problem. And the artifacts that you see over here is simply because we never observed that portion of the data. So it just contains some random model stuff.
So Andrea, it sounds like you're the Grim Reaper. So I'm just wondering, in terms of just getting back to your analogy there, but is there any relevance to the Gaussian splatting at this point then?
Oh, what?
Is there any relevance to Gaussian splatting?
So the one thing that I do not know is that this representation, if you think about modeling like a foreground object, you still have to have the volumetric bit surrounding it. So the one advantage still of Gaussian splatting is that you don't need to represent empty space. Well, in our case, you do. However, because we are representing empty space, we actually don't have convergence issues. Because when you have a cell that covers empty space, it means anywhere in the environment receives a gradient. Versus in a Gaussian splatting representation, gradients are compactly supported. And so you have, I don't know, the thing is, the question you asked is like, on one side, you get some wins, on the other side, you get a lot of losses. So, and honestly, I don't know. It depends whether we can actually solve these other problems and make it work properly. I have no idea. I don't know how to answer.
Early days.
It's I don't know. Yeah. So actually, the one, for example, the one you asked, what is it? So this one, for example, is trained from random initialization. And if you see the garden scene, this one, and actually it's exactly the same PKSNR. I mean, it doesn't work all the time. Sometimes you get a little bit of a loss, but more or less is invariant to initialization, just like the MCMC solver was. And this comes from the fact that these Voronoi cells cover the environment. And so you basically have globally supported gradients, not locally. Right, so in terms of, there's not a lot of stuff moving, right? So densification and pruning to increase or decrease. So you can see what the numbers mean down here. If I don't densify, it looks terrible. If I don't prune, it looks more or less the same, but of course the representation will have a lot more sites than needed, so it will be inefficient. The quantile thing is mostly used to remove these like floater artifacts that are very commonly present in all NERD backends. And then in terms of performance in comparison to external models, it's strictly better than 3DGS. There is some new versions. So 3DGS MCMC was the state of the art in terms of 3DGS models until a while ago. And then a week or so ago, there was this paper whose name I don't remember that came out, which has this funky, more higher dimensional Gaussian, I forgot. Does anybody remember the name?
Deformable beta splatting.
Yes, the deformable beta splatting, which has this generalization of Gaussian that gives you an extra bit of PKSNR. We'll get there. And that's where the V1 results stand down there. We're still iterating on improving the quality. And yeah, so here you can actually see, for example, papers that kind of were trying to achieve a very similar result. But remember, any of these will still require you to have a CUDA GPU. There's nothing whatsoever in what I show you today that could not run in a shader. And so all of these other things that people have been working on, they're limited to CUDA implementations. We have done a similar trick in Wallnerf. This is completely independent of the architecture. And as of a few days ago, I think I'm done, right? Start of 10. As a few days ago, we launched the code. It's out. People have already actually been using it. We actually have a much larger scene than we ever trained. So this is a live video from YouTube. I've never done this before. It's actually playing from YouTube at the moment. It works.
Thanks. And then a scene like this.
This one I have no idea because I didn't train this. The other ones is typically in the order of a few millions. It's very similar to Gaussian splatting representation. This looks much better online than it does on screen, just because of YouTube compression. But yeah, in terms of future research, it's like, remember I had this slide? So I'm going to be lazy and I'm going to put the same slide on again. I'm not going to go anything from the internals and make it more efficient to like better viewers to literally like re-going again, like Vision likes to do every 2 or 3 years. Something new comes out and then you go down the list, revisit paper from 2 years before and redo everything from scratch. I'd like to thank again Shri and Daniel for a lot of sleepless night with CUDA and Kwan for being an awesome collaborator as usual. Pixely.